CLM. And in particular, one of the characteristics that I think is fairly peculiar is that that land model represents separately what happens in urban areas rather than rural areas. So when we look at heat extremes, we can separate how those change in an environment that is cement and roads and high buildings from what happens if you live in a more suburban or even rural setting. So we have a study that looks at changes in extremes separating those two aspects, and then we feed those results in a different study that matches what happens in terms of changes in heat extremes to two scenarios of growth in population. And this growth in population is actually resolved spatially, so you can actually match the changes in extremes at different regional locations to the projected changes in population in the future. This is a study that was actually just published. It was the last one of the group. And then different studies zoomed in. So the first one I mentioned looks at what happens globally and compares very large regions of the world. And other studies zoomed in over the US and actually tried to translate these changes in heat extremes, not only into exposure of population to those extremes, but also impacts in terms of mortality, and in particular, high mortality events. Another study, always in the same category, focused on Houston and studied much more specifically in a fine scale how Houston characteristics in terms of socioeconomic development and vulnerability aspects impact the outcomes in terms of health. So this gives you a little bit of an idea of the kind of studies related to heat extremes and human health. This is just to show you that depending on the scenario, RCP 4.5, RCP 8.5, exposure to heat waves that here is measured in terms of billion person days per year. So we match the days that belong to a heat wave in the future to the people, the number of people that are exposed, change dramatically from present, of course, which is the gray box that you barely see there on these scales, to much larger numbers of exposed people. Of course, much larger under RCP 8.5, like the red boxes show. But you see two boxes there because, as I said, we were matching these projections to different projections in terms of population growth. The future is not deterministic, and we may have scenarios where the world develops faster in terms of wealth, and we know that when societies get richer, the fertility goes down, so there may be very large differences in the number of people living in the future in certain areas. And so this gives you an idea of the impact of that factor on the projections of exposure. I forgot to look at my watch, so I'm wondering. So the other example that I want to go quickly through is something related to agricultural impacts. Again, we start from the output of the model in terms of changes in temperature and precipitation. And we look at how the land model produces changes in agricultural yields. So this is a process model that is nested into our NCAR climate model, and on the basis of those changes in climate, will produce changes in productivity of plants, and among those plants, crops that are relevant to food security, for example. So this was a study that did just that. And then using a so-called integrated assessment model that puts those changes in agricultural yields into an economy and relations between regions of the world, we determine changes in the price of commodities, and we're able to characterize effects on food security and prices in general, but also land use allocation on the basis of that model. Now, you can go at it this way with a process model. What I like to do being a statistician is determine this kind of impacts from a statistical model. And so we have also a study in there that simply looks at empirical relationship between temperature and precipitation and crop yields. And you can compare the results between a process model and an empirical model, which are numerically different, but in terms of direction of change, agree fairly well. Okay, so I have the main conclusions. I'm hoping to be more or less midway through. And what I want to summarize here is the fact that we compare these two scenarios. We see substantial benefits to mitigation between RCP 8.5 and 4.5 under many aspects. Of course, heat waves, as you can imagine, are much less devastating under RCP 4.5 than 8.5, not that they are good, but US population exposure to high mortality sees large benefits of mitigation. Maize and wheat exposure to extreme heat, of course, being again related to extreme heat, see very large benefits of mitigation. The likelihood of major slowdowns in the production of important crops around the world sees this kind of benefit. And measures of aridity and drying show very significant differences between these scenarios. Now, what maybe is interesting to know is that there are aspects of changes where we don't see this significant difference, even between two scenarios like RCP 8.5 and 4.5. And these, sorry. I don't know what's going on here. I can squint and tell you, but is there, oh, okay, maybe now, yeah. There are aspects of these changes where these benefits of mitigation are not as, striking, and they have to do, for example, with crop yields when you introduce the effects of CO2 fertilization, or, population exposure to things like dengue dengue carrying mosquitoes. There it's the societal evolution that is much more relevant than what happens between these two scenarios in terms of changes in the kind of environment that favors these vector-borne diseases. And for global tropical cyclone track densities, we don't see significant changes between the two scenarios when you account for internal variability. Okay, so now for the Paris Agreement related analysis. So again, the idea was to compare now these scenarios that, if you think about, are very, very close to each other. It's half a degree at most of differences in global average temperature between what used to be the accepted number of 2 as the dangerous level of anthropogenically induced climate change, and the new target that has been posed as significantly lower than that, and ideally 1.5. Again, we look at different aspects, and I'm going to focus, depending on the time, on these two topics, one having to do with the changes in extremes in the physical climate, and one having to do with agricultural impacts. But first, just a very simple picture of what you can expect under a scenario that reaches 2 degrees of change under global warming. That is surface temperature change as the ensemble mean of our ensemble. You see that, of course, there are areas that see changes that are much larger than 2 over land, specifically in the northern hemisphere. What you see in the second panel is the difference between 2-degree scenario and 1.5 scenario. So here I'm showing you much smaller differences, of course, but since you see dots everywhere, it means that those differences are actually statistically significant. So it's not internal variability that produces an output different between 1.5 and 2, but there is a robust result there. while if I show you precipitation, the picture is much different. You see changes that are statistically significant under the 2-degree scenario. When you compare the two and talk about the differences between 1.5 and 2, you see that we have much smaller areas that are covered in dots, meaning that only those areas show a significant difference between the two scenarios in average precipitation. So we went, yes, thank you. So we went about looking at extremes, indices of extreme, and extreme temperature and extreme precipitation, and something that we called agriculturally relevant extremes. Many of you will recognize these definitions. They are a subset of the ETC-CDI indices. And our question was, okay, we know what happens on average to precipitation and temperature. Can we say something about the changes in indices of extremes? And what I'm going to show you are maps whose scale doesn't have to do with temperature or precipitation. These are number of indices. So I showed you before that we had 4 indices related to precipitation, I believe 3 related to temperature and 3 related to agriculture. And the color of this map is telling you how many of those indices are significantly different between the two scenarios of 1.5 and 2. And so to our surprise, even precipitation that we know has a lot of noise built in, shows large areas where some of these indices are significantly different between the two scenarios. That's the map up there. The agricultural indices, 2 of them are frost days and growing season length, so they are related to temperature, so it's no surprise that at least 2 of them are strongly, significantly different over large areas. And you can guess because why I'm not showing you the map with the temperature indices. It's because it would be totally red. So all the indices related to temperature, like the changing coldest day of the year, the changes in the hottest day of the year, the changes in warm spells, show all significant differences across the entire land regions under these 2 very close scenarios. Let me skip these 2 maps and go very quickly through these changes in crop yields under these 2 scenarios. And the reason I want to do this is to give you a sense of the range of results. So when you talk about temperature in particular, but in general when you talk about the physical climate changes, it's a little easier to put your hand on numbers and statistical significant results. When you start talking about impacts where either processes are more complex or you have to take into account things like adaptation and the effect of human development, things start to be a little foggier. So this is an example of the foggier results, as you can see also from those trajectories that are a little shady. So what I'm showing you here in 3 different colors are the changes in temperature over the regions that grow either maize or corn in the 2 panels, and over a critical period of the growing season that we find extremely well related to the yield, the eventual yield. So the idea is that we estimate these changes from the climate model, we feed them into our empirical model that relates climate to yields, and we determine what these changes in temperature translate into when it comes to crop yields. And that's the next picture, which is almost perfectly a mirror of the first one, where we see these are percentage changes in crop yields. It doesn't matter the number, they are small numbers. They are around 5% there in the lower part of the graph. But what is telling you is that these crops respond very directly to changes in the warming of temperature. So warmer temperatures are not good, at least at the global aggregated level, which this is, for crop yields. So on the basis of this picture, you would say, well, actually I can see that the pinkish trajectory is a little higher, so it seems like this 1.5 scenario is actually beneficial rather than the 2-degree scenario, which is the green, which is lower, especially for maize, which is the lower panel. But here I'm not including CO2 fertilization. When you include that, the picture becomes much more squished, and especially for wheat, the first panel, you see that all the trajectories now are one on top of the other, meaning that the effects of CO2 fertilization, given that CO2 is higher under 2.0 rather than 1.5, makes up for the difference in temperature, at least for wheat, which responds strongly to CO2 fertilization. For maize, you still have a difference, but it's a small difference. Now, there is a lot of uncertainty in the effect of CO2 fertilization, and even maybe for these scenarios, not as much as, for example, for RCP 8.5, because we are still, thank you, we are still at levels that are fairly close to what we have now, but in general, it's one of those processes that is not pinned down extremely well, and that's what I was trying to hint to when I'm saying that as soon as you start talking about impacts, you have to take into account a lot of other dimensions of the problem that make the characterization of a quantitative change much more challenging. I'm not saying that the physical climate characterization is that easy, but relatively speaking, we are adding complexity. So what, maybe it's a more straightforward thing, but you don't see very much differences when you think about the exposure of these crops to heat extremes. It's obvious that heat extremes are bad for crops if they happen at a certain moment in their growth, the flowering season. They can destroy a plant completely. So the fact that you have more or less extreme heat, even if it's a smaller difference, can be beneficial to a certain crop in a certain area. But at an aggregated level globally, the changes are very small. They are barely visible on these maps that shows you the differences in heat exposure of the areas that grow these crops between the two scenarios of 1.5 and 2. Okay, so I think I got to the end. And the conclusions for this particular comparison of 1.5 and 2 scenario impacts is that for temperature and precipitation, we see some fairly significant differences, both in the means, especially for temperature, but also for many measures of extremes, even those that relate to precipitation extremes. And for agriculture instead, when we aggregate at the global level, these differentials are much more subtle if they exist at all. Okay, so this is my conclusions. What I wanted to say is that, I feel like it's always good to present things in terms of alternative scenarios from a communication purpose. I feel like people like to see that there are choices and compare results, and I feel like it's a little empowering, at least, to have alternatives in front of us. So I like this framing. And I was actually surprised, after we started looking at this, that we saw so many differences, at least statistically significant. Now, how that translates into actual impacts may be less immediate. But even between these low warming scenarios that are so close to each other in terms of global average temperature. And as I was trying to say, when you start looking at actual impacts on society or human or natural systems, you start getting into a lot of complexities that we are not yet very good at characterizing. So I feel like it's an interesting area of research, maybe not one that all of you are ready to embrace, but I find it very interesting and compelling. And I think I'll conclude here, except before somebody asks me, these studies were performed with one climate model, even if we love it because it's the NCAR model, at least I'm supposed to. It's one. So we are looking forward to the new simulation from CMIP6, where these scenarios will be explored by a set of many models, and we can see how robust these scenarios are going to be once we compare across the community of models. And thank you for this opportunity.
Some microphones going around. Do you have any questions for Claudia?
Gavin, or?
Yep, Gavin. Sorry, I didn't see you.
Thanks very much. That was really interesting. Your special issue covered a few areas, and it kind of makes intuitive sense that perhaps rainfall is not going to be that different, but something like sea level might be quite different. Can you kind of comment on, across all the different studies, what was the biggest difference between 1.5 and 2?
Oh dear. I think the biggest and more robust differences are definitely anything to do with heat extremes. There, the signal is emerging. It's emerging very quickly, and it's incontrovertible. For sea level rise, I think you would have to look much farther in time than just the 2060, 2080 horizon that we were looking at, because it takes a while for the whole system to respond and to see the differences. Let me think. Yeah, I think I go back to the heat extremes, which are also our favorites because they always pop up.
You almost answered it just then. I was going to ask about sea level rise, right? So the 1.5 came about because of the small nation states,
right?
And they care about sea level rise. So do we have the tools that allow us to say what the risks of meter plus sea level rise is and how that might change under these different scenarios?
As you know, even better than me, climate models don't do it, right? They cannot represent all the processes. One of the largest uncertainties come from the behavior of ice sheets, and particularly this dynamic behavior that it can be, abrupt, and like we know, Antarctica can shed, these enormous pieces of ice unpredictably. And our models are just not able to represent those processes, even if we start, the work by Robert De Conto. And so I feel like sea level rise, it's this kind of, it would be probably the poster child for this kind of analysis, because it would probably be the most compelling result. And as you say, it was motivated, the Paris Agreement, by the push from small island nations, but we just don't have, I think, the robust tools to address that. That's my feeling, but I'm not an expert on sea level rise.
Hi. Yeah, my question is concerning about the representativeness of these indices. So you said that it's quite challenging to use that in terms of impact. So I would like to see from you, how do you see in the future? Do you think it's more reasonable to do those customized indices? What do you think about that?
I think there is room for both. I think there is room for this kind of general and global, large scale, a little superficial, without diminishing, the work of people that look at these indices. But this big picture metrics, I think, have a role. When it comes to actual impacts, I think it's really important to talk to the sectors that are impacted and try to elicit metrics that are more directly relevant. But it's very hard, as you can imagine, because every impact has a peculiarity, and so every outcome needs to be characterized by a metric that is fairly specific. And there is a lot of work in the community. I was at a workshop the past summer that tried to make inroads in that direction, but it's a very complex enterprise, and maybe there is value in specific studies that focus on an issue, on a region, a sector, and try to characterize that well for actual decision makers. And I was looking there, hoping that the question came from there, but I couldn't see.
Hi, I'm just wondering, with your the impacts on agricultural yields being, muted by the carbon fertilisation. There have been some studies that have shown that nutrition is impacted. So while they're high in carbon, they're not high in some of the trace metals, for example, iron. I wondered if that would be possible, or if you know of doing that work.
Yeah, unfortunately, I have to say I'm not an expert. I rely on David Lobel, who is my co-author for this part of the study. So I'm afraid I cannot answer that satisfactorily. If it is Amanda.
One more quick one, or
Maybe we should run
Yeah.
to our.
so if you want to hear more from Claudia, she's giving a talk in the next session. So we
Right
thought we'd
now.
give her a few minutes in Matthew's 8 to get there. But please join me in thanking Claudia again for a great talk.